Good afternoon, everybody. My name is Michael Martin. I'm the engineering manager in Réaltra Space Systems. We're a small SME company based in Dublin. We've been in existence for about the Themis launcher. So I'll give you an overview of both Réaltra and what we've done as part of the SALTO project. So just to give you an idea of the space heritage from Réaltra, say we were busy 7 years. We started from nothing to develop our space heritage. We are involved in the European Space Agency Plateau mission. We've just delivered our flight units in test at the moment and will be launched in December next year. And this is a payload interface module which will control the temperatures of the 26 scientific telescopes to a very high accuracy of plus or minus 15 Kelvin. And this sets the fine focus of those telescopes. So it's obviously a mission critical device. So we're very proud of being able to deliver that and successfully integrate onto the satellite. We've also developed an acquisition system for the International Space Station. It's used on the European Columbus scientific module. And there we measure all the different environmental conditions when they're doing experiments, particularly the microgravity levels. Obviously, we're involved in the SALTO project. Also with Ariane 6, we supply a video telemetry system for the Ariane 6 launcher. And I'll tell you more about that in the coming slides. And we've built up a product range of avionics systems particularly for launchers. And this is a full turnkey system, autonomous system. So we take no resources from the satellite or the launcher, from supplying the battery power to our battery system, the power control system and protection system, to the RF transmissions to transmit the information down to the ground stations, the data acquisition systems, the high definition video cameras. We also have a GNSS navigation receiver, and we've developed a cryogenic camera that can be used inside the fuel tanks. In a network switch. Just some of the images we have received. We're very proud of these images. On the left-hand side there, we have the image of the James Webb telescope, just seconds after separating from the Ariane 5 rocket. This is a very iconic image shown all over the world. It's even used in Queen, the rock group Queen have used it in one of their pop videos. It really, there was a lot of history in this from the point of view that it proved that the Ariane rocket actually inserts satellites very accurately in orbit. Because within minutes of this image being taken, we could see the solar cells deploying. And that was automatically happened on the James Webb telescope once it was in the correct position. So within less than a minute of deployment from the Ariane 5 rocket, it was in the exact position. And that saved a lot of fuel for readjustment of that orbit and increased the lifetime of the James Webb telescope by 10 years. So just this little image and this video that came from this was a really good demonstration of how good the Ariane launcher system is. In the middle image there is the first flight of the Ariane 6, the new Ariane 6 rocket, and we can see the separation of the boosters. And then on the right-hand side here, it's our AI-enabled camera that's flying in space now for over 1.5 years with an American satellite called Eris. And just the bottom image there of that is actually flew over Ireland just last month, and we got an image, some sort of an image of Ireland. As usual, Ireland is covered by clouds, so it's very hard to get a clear image of Ireland from space. Just on the Ariane 6 video system, so we've got a lot of really, really good images through our video system, the different stages, all the different separations of the boosters and of the first and second stage. And these are great from the PR point of view, but from an engineering point of view, there was a massive amount of very valuable information here. This is the first time the Ariane 6 launcher flew, so the engineers from Ariane learned a lot of information due to the high quality, high definition videos of the different stages. And that was very valuable to them in future flights. Our next flight is actually next Tuesday. So we're looking forward to that with the launch of a Sentinel satellite. Just from the SALTO point of view, then we used all this kind of knowledge and heritage we built up to develop an improved high-speed camera. And during the program then, we also developed a 12-channel network switch to help integrate the video camera, obviously, and 8 other parts of the payload. Both of these now are integrated on the top of the Themis rocket up in Kiruna. So again, we're looking forward to that first hop, and hopefully we can add to our iconic images during that historic first flight. On the camera itself, Réaltra specialize in adapting COTS, that's commercial off-the-shelf electronics for use in space. For launchers in particular, there's a lot of shock and vibration. So we've qualified both the camera and the network switch to the highest levels for launchers, particularly the Ariane 6 launcher. So we did thermal cycling, thermal vacuum to very low levels, sine and random vibration to the high levels of 35 G RMS, and pyroshock to 5,000 Gs, and obviously electromagnetic compatibility testing. During the flight of a launcher, you go through different phases where you get very high shock levels when you have the separation of the different boosters and the stages, and so your product is hit badly during those shock periods. So that's why we specialize in being able to develop the electronics to survive that shock. And on the features of it, so we improved a lot of the features of it compared with what we're using on the Ariane 6. So we've got at the top level of high definition imagery. So we can see during the launch hop, we can look at and analyze the video later on and see all the structural and subsystem behavior during that flight, and also particularly during the landing. We also concentrated on low distortion of the images, because a lot of these images we're looking at very fast changing, just very a thump to the legs when it lands. We want to be able to see all those very clearly, and you can see there just a little demonstration of giving you a little image there showing you the different ones. So we've used global shutter technology here, and that image on the left there is a fan spinning at high speed, and it's perfectly formed. But the image to the right of that is through a standard commercial rolling shutter type sensor, and you can see a lot of distortions there at very high speeds. So that's a very important factor for this, for the Themis, so we can see all the shocks and vibrations and clearly see how all the different structures and sub-assemblies are affected by those. We also have used a compression technology, the latest compression technology of H.265, and that gives us a good compression, an efficient compression of the high definition video. Kilobits per second, we're able to send down full HD quality video. So that makes a big difference, particularly in deeper space missions where the RF link is much lower. We've obviously reduced the latency as well, which is important. On the optics sides then, again, distortion, very important. So low distortion optics we've used with a wide angle view. This can also be configurable. So we can put different types of lenses, to narrow lenses to home in on particular items you want to see, or very wide angle fish angle lenses. For this flight of the Salto, we have picked the wide angle 90-degree field of view lens. The other part of it is the 12-channel network switch. We developed this in partnership with TTTech in Austria, and also partly funded by the European Space Agency FLPP program. And this has 4 1 gigabit Ethernet channels and 800 megabit channels. We can expand that to 20 if needed, but 12 is sufficient for the Salto program. But it also covers all the different types of Ethernet traffic. So we have best effort, which is just your standard Ethernet traffic. We also have time triggered Ethernet and rate constraint traffic. This is also flexible, that we can combine all of these, so you can receive in the best effort standard Ethernet one, but you can send it out as time triggered Ethernet, or you can receive time triggered Ethernet and send it out as rate constraint traffic. So very flexible, very easy to configure and use. Security, obviously a very important part of it. So we're very safe partitioning between the different ones, between the rate constraint and time Ethernet traffic, and also very high reliable, fault tolerant with a high bandwidth utilization. So just a quick overview then on the roadmap going forward. The Salto project enabled us to develop this new high-speed, low distortion high definition video system, but it also helped us reduce the weight significantly by 40%. Our cameras are now, these cameras on Salto are now down to 340 grams, and we've also been able to reduce the cost of them. So now what we want to do is combine all this what we learned over the FLPP project and the Salto project to produce a highly integrated, configurable avionics system, particularly for small launchers at reduced cost. So we can, with the base unit of the network switch, we have the base unit there, which is in a PC104 small footprint, and we can stack that up in a stackable format, and we can add in then, include in there the battery power and distribution into the system. We can put in a GNSS navigational system in it. We can put in an RTU to look at different types of sensors, from strain gauges to accelerometers to smart sensors to wireless sensors. And we can also include in the encoding, the CCSDS encoding, which is needed for the RF transmission down to ground stations. And then, of course, we integrate as many cameras we want in that system as well. So it gives us good flexibility going forward, which will be a very attractive proposition, particularly to the new space and the small launcher market. So we're hoping that we can develop this further from that. Okay, that's everything from my side. Thank you very much.